All right, part 2. So we left off with that idea that, if you have a certain thing, in this case a coin, it has 2 outcomes possible. When you do the flip 2 times in a row, you got 2 outcomes on the first, another 2 on the second. 2 times 2 will give you those 4 total outcomes. And if you use this tree diagram approach, you will always be able to get down to the ends of the branches here that got underlined in red and have the total number of outcomes represented. So even though you got to work your way down the branches to get the full outcome, like heads, the number of branches at the very end will represent the number of outcomes total. So also note that each time you flip the coin twice would count as 1 trial of the experiment. And, if I were to flip a coin 3 times, if that was my, thing I was working on, well, then flipping it 3 times would be 1 trial. If I, go back to this one where I'm flipping it twice, I flip it twice, that's 1 trial. I flip it twice again, that's a 2nd trial. Flip it twice again, that's a 3rd trial, etc. So there's, these trials, there's different things that you can do in succession to satisfy 1 trial of your experiment. All right, now getting to the events, there are many events that might be of interest. And it depends on the question that is being asked by the people running the experiment. So one example of an event for 2 coin flips would be where the result was 2 tails. So you would look up at the sample space and say which event, or I should say which outcome satisfies that event. And you look here and you say, oh, there's 1 outcome with 2 tails, so that satisfies the event of interest. So there's 1 out of 4 for the probability of that event. Another event might have more than 1 outcome in it. So for example, if you're like, what's the probability of seeing heads and tails when I flip this coin 2 times? I want to see both a head and then a tail, or maybe a tail and then a head. But you would just say, heads and tails show up. Well, looking up here at the sample space, there are 2 outcomes, that would satisfy that event of heads and tails mixed together. So then the probability there would become 2 out of 4. So your event can be just maybe 1 outcome, or it could be 2 or more, depending on what you're looking at. So one thing that we're going to see here, that gets kind of glossed over is this idea of fair, and when we talk about fair coin. So let's focus on that a little bit on this next page. So note that I used that word fair in the last example. I just noted that. So in probabilities, it is important to know whether or not the outcomes are equally likely before you can calculate the probability of an event. In this class, our focus will be on experiments where the outcomes are equally likely. It's a different level of probability where you start working with events that are not equally likely. Again, we don't go deep enough into it in this class to go there, but it'd be something like if one side of the coin showed up more than the other, was weighted so that it showed up a different way. So maybe instead of 50-50 chance between heads and tails, you're looking at maybe 3 times it's going to come up heads, 1 time it's going to come up tails on average every 4 flips. That's going to be an unequally likely distribution between the 2 sides. Another example would be like a die. If you have a weighted die, maybe you have the number 6 rigged to show up more than the other numbers. Both those things would get you taken out into an alley in Vegas and beaten. But, we're not going to look at them for just mathematical curiosity here. Unfortunately, they are interesting in how they change the probability world. But what we're going to focus on is things that are equally likely at this point as we introduce the probability concept in this book. So finding probabilities then, moving into this, when there are equally likely outcomes. Well, overall, there are three ways to compute a probability. A theoretical probability is based on the mathematical model where all outcomes are equally likely to occur. You can think of this as what should happen. This is based on knowledge of the possible outcomes, your sample space, based on the number of outcomes that satisfy the event of interest. And then you can put together your theoretical probability. An empirical probability is based on an experiment or observation and is the relative frequency of the event occurring. So this is where you actually went out, you took the coin, you flipped it a bunch, and you're collecting information on what did happen. And then you're able to make probabilities based on what did happen, not what you thought should happen, what should happen, but what did happen. And we'll see there is a relationship between theoretical and empirical as we move forward through this chapter. But overall, at this point, I want you to understand theoretical is what should happen based on mathematical understanding. Empirical is what did happen as you were actually running the experiment. So a subjective probability is just an estimate, a guess based on experience or intuition. So, it'd be like you go to a mechanic because your car is acting up, and maybe, you're a little low on the funds and you're waiting for your check to come in. So you're like, hey, mechanic, what's the chances my car is going to last until, I get paid? The mechanic will, look at your car and, figure things out, think about it a little, and based on their experience, come back to you and be like, hey, maybe you got a 50% chance that your car is going to last until you get paid. It's really not based on them figuring out all the possible outcomes, all the events of your car not working, and then making a probability. They're just going off of their experience. So, that's an example of subjective. We won't deal a lot with subjective in this class, but that is one of the three ways to compute it. So this class will focus on theoretical and empirical. We'll see more about how they relate to each other later, as I said. For now, just need to understand that both of them use the same basic formula to determine the probability, i.e. a fraction. So, for what we're looking at here, an experiment has equally likely outcomes. Every outcome has the same probability of occurring. Like with a coin, it's a 1/2, 1/2. For each side, for a die, 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. For equally likely outcomes, the probability of an outcome A, probability of A, is P of A is the number of ways for A to occur divided by the total number of outcomes. So round off rule, you give probabilities as a fraction or as a decimal number rounded to 3 decimal places. That may change in the homework a little bit. Sometimes I'll see them go to 4, sometimes 2, depending on who wrote the program. But I took a class where the teacher was adamant that you always went out 4 decimal places, so that might change a little. But basically, you can write them as a fraction, and you're going to be just fine in most cases. All right, so number of ways for A to occur, total number of outcomes down below. So for the following example, it's going to be really helpful to know a standard deck of cards. And again, I grew up in Las Vegas. My dad dealt cards. My mom worked in a casino. I knew a lot of friends whose parents worked in casinos. And if anything, growing up in Vegas, people were aware of casinos and card games. And then I moved away from Las Vegas, and it was kind of surprising how few people actually know what a deck of cards is once you get outside of Las Vegas. But in a deck of cards, you've got 4 suits. So there's 4 suits: hearts, diamonds, clubs, spades, in order there. There are 13 cards in each suit, from the 2 all the way up to the ace. there are 4 of each denomination. 4 2s, 4 3s, 4 4s, all the way up to 4 aces, which is a very good poker hand if you're playing 5-card poker. So 4 of each denomination. And then there are 26 of each color, unless you're playing with some weird funky deck. There are 26 red and 26 black in most standard decks of cards. And a face card, I wish this little deck that I pulled off the internet had faces, but the Jack, Queen, and King cards are the only cards that are face cards. If it's got a face on it, it's a face card. And unfortunately, as I said, this particular deck doesn't have faces. But aces never have faces. Only the Jack, Queen, and King will have faces. So there are 12 face cards overall in a deck of cards. So the first example here, you pick one card from a standard deck of 52 cards. Consider the aces high, so they are bigger than the kings. What is the probability of the following events? Picking a king, picking a heart, picking a card that is less than or equal to 3. That's why aces high is important here. So I want you to pause and think about those 3. All right, welcome back. So 52 cards total. So I know the denominator is going to be 52, and I'm going to start writing out the notation for this. So picking a king, we have the probability of a king. That's our event of interest, outcome in this case of interest. And you would have 4 kings in the deck. So that's the number of ways your event could be satisfied. There are 52 cards total in the deck. You reduce that to 1 over 13. And that would be your answer. For picking a heart, well, there are 13 cards in each suit, so 13 hearts. So your probability of a heart is going to be equal to 13 out of 52, and that reduces down to 1 over 4. And then last but not least here, picking a card that is less than or equal to 3. So that's only the 2 and the 3. You pick anything outside of that, all the way up to the ace, it's not less than or equal to the 3. So there are 4 2s, 4 3s. There would be 8 total cards. That would be less than or equal to a 3. So this will equal the 8 over 52, and that reduces down to 2/13. So the P out front here of these parentheses is standing for probability of whatever's inside that parentheses, and then you find the numbers that you need to make the fraction. All right, so let's see, we got a little bit of time left in this video. So let's go over here. Now that we've computed some probabilities, you should be aware of a few facts about the results that you might see before we move on. Probabilities will always be between 0 and 1 inclusive. You'll never have anything in the negative side because it makes no sense when you're counting the outcomes to get a negative number. You're counting things, you're going to get positive things. So you'll never see a negative probability. The 1, that's like 100%. Well, you're never going to see like 53 cards out of a 52 card deck. That makes no sense. You're never going to get more outcomes than the total for your event of interest. If you did, you counted wrong. So you'll never see a probability bigger than 1, bigger than 100%, always between 0 and 1 inclusive. So you could see 0, you could see 1, but you won't see anything less than 0 or greater than 1. The sum of all the probabilities of a given sample space of outcomes will always be 1. When you add together all the probabilities in a situation, they should add up to be 1 as long as you got everything accounted for. So like with the coins, you had 1, 1, 1, and 1, 1/4 plus 1/4 plus 1/4 plus 1/4 for those 4 outcomes equals 4 over 4 or 1. pick up in part 3 with the rest.